realized that they were getting perfect results, and so during the lab, they called me over and they said, just want to let you know what we've done, because we're getting perfect results, and I want you to know that we're not fixing it to get that, it just happens to be working out. And then the group took me through what they were doing, and it all was above board. It's one of those rare times. All right, so part of the lab is you're gonna, this thing is the second part, you're gonna have some hanging mass here, and then you'll just add masses to that to change the overall mass that's moving, keeping the force the same. You can do a plot, see if this is how close the slope comes to that force. And then the other part of the lab, we're gonna keep mass the same and just change the force. Let's think about how we could do that. How can we keep, questions here before I go off with this next part? All right, so how can I keep the total mass the same but change the force that's driving it all?
The box that would be going down would weigh more.
Say it again?
The box that's going down would
Yep.
weigh more.
Okay, but I want to keep total mass the same, so how do I do that?
Would you take it away from the little part?
Absolutely. And so the other part of the lab is I've got a certain amount of mass involved, and I keep it set, and then I run a trial, and then I take one of the masses and then move it to here. So now the total mass stays the same because whatever mass, well, because that mass plus that mass should still be the same, but I've changed the force here. So now when I plot, and I don't need the grid for that, I'm going to be plotting acceleration versus force. If I plot acceleration versus force, well, I'm still basically dealing with the same thing over here. It's just that now my x value is force. And so this is acceleration is 1 over mass times force. That's my slope this time. So my slope, so you get the data points, you do a trend line, you find the slope because it'll be in some form of y equals 7x plus 0.2, whatever it happens to be. That should be the reciprocal of the mass. So 1 over the mass is equal to 7, so the mass would be 1 over 7. Obviously, making these numbers up here. The lab that you're going to be doing gets good results if you take your time. And then there's one last place that students tend to make a mistake. So questions about, because we need to figure, we're going to be measuring acceleration. The question is, how do you measure acceleration? So that is the last piece of this lab. Questions? All right. If I took, let's flash back to, actually there's an equation we did. We talked about last time that Hewitt has the constant velocity equation, or constant speed, whichever way you word it. It's constant velocity equation, and so displacement was velocity times time. So again, displacement, he worded it differently, but this is in essence. This is acceleration is 0. He also had the free fall when the initial velocity, so if the initial velocity is 0, he had that the displacement is 1/2 kT squared. We talked about this last time. And then there's the general equation that works where we don't have to make those assumptions. We still assume acceleration is constant, but where we have displacement is equal to the initial velocity times time plus 1/2 kT squared. I'm hoping this brings back some fond memories of Tuesday. No one's giving the nod of, or the smile that says, ah, good times. Okay. I'm gonna change this around just a little bit. This is final position minus initial position. That's just the change is equal to all that. I'm gonna add initial position to the other side. So what I end up with is x final. So my final position is just my initial position plus my initial velocity times time plus 1/2 at squared. I'm gonna write it slightly differently because if I'm looking at, if time is my dependent and x is my, if time is independent and x is dependent, I'm gonna drop the vector notation. I basically have this position is equal to some initial position plus term, actually I want to write it in other order. So I got 1/2 a t squared plus some initial velocity t plus some final, or some initial position. So I got some squared term there, some squared term there, or linear term there, and basically my function. All right, I know we've got a wide variety of math abilities here. What would this equation look like if I plotted it? Or in a more traditional form, y equals ax squared plus bx plus c. Well, what is that an equation? I know some of you have seen this before, or I feel very confident.
Parabola?
Yes, it's a parabola. What's a parabola look like? Dean? No, I thought you were about to make a gesture with the pencil.
Upside down U.
Or, one way or the other.
Yeah.
Now, as that cart is moving down the track, we should be able to describe the displacement or the position based upon this formula here. Acceleration is constant, so this actually should be true. Which means while that cart is moving down the track, my position time graph should look like a parabola. So if I put a motion sensor right here to track that cart as it moves down, what the graph will look like is this is my position and time. It's not moving, and then suddenly it's going to look something like that. This is before you let go of it. This is after it crashes into something. Please don't let it crash into the pulley. This is after it hits something. But we got this nice smooth part of the parabola right here. And this is in the instructions. What you're going to do is you're going to highlight a section here. Part where it's not hit anything and you've let go of it, so somewhere in there. And you're going to do a curve fit. Now, that's one of the functions. There's the words at the top. The middle one is graph. I think the last one is analysis. You click on analysis, then you do curve fit, and you say, I want to fit it to a quadratic. This is a quadratic. I know I've read somewhere why they use the word quad when it's squared, but I'm blanking at the moment. What the LabQuest is going to tell you is it's going to show this equation and then it's gonna give you a value of capital A, capital B, and capital C. Then it's gonna give you something known as the RMSE. I can't remember if I asked you for that or not, but if I do, this is the root mean square error. You want this to be as close to 0 as possible. The root mean square error is, I got data points, I've mapped the curve to it. How good of a fit is it? Now, you've done something similar to this when you created the graph and you said make a linear fit, and it gave you an R squared value. There is a relationship between R squared and RMSE. R squared, you want closer to 1. RMSE, you want closer to 0. They're both measuring error. But to find acceleration, recognize that in front of this squared term here is 1/2 times the acceleration. The LabQuest is going to give you this number. So this number should be half the acceleration. So if it gives you 0.72 for this capital A, then your acceleration, well, that's half the acceleration. So your acceleration is twice that. Biggest mistake I see students make, if they've done the lab perfectly up to there, is forgetting to multiply this times 2. So please don't forget that. I think it's even in big print somewhere on the lab. So if you end up doing it and you are 40% off and you feel like you did the lab right, check that. Questions to hear? All right, now I got you pumped and excited for doing this lab. Feel the energy. I think it's time to go down there and do this lab. The door's locked right now, so I'll go unlock it. But the labs are sitting out on the table. Just grab one of the stacks.